Dr. Andrew Huberman reveals how sounds and balance can transform your brain's potential. From binaural beats to dynamic movements, unlock simple, science-backed tricks to supercharge your mind. Watch now and change how you learn forever. In the realm of neuroscience, the auditory and vestibular systems, responsible for hearing and balance, respectively, play critical roles not only in sensory perception but also in cognitive enhancement. Dr. Andrew Huberman, a professor of neurobiology and ophthalmology at Stanford School of Medicine, emphasizes that these systems interact dynamically with other brain and body functions, offering powerful tools to accelerate learning, improve focus, and enhance memory retention. By understanding the biological mechanisms behind hearing and balance and applying practical strategies such as binaural beats, white noise, and vestibular exercises, individuals can optimize their cognitive performance. This article explores these concepts in depth, drawing directly from Huberman's insights to provide actionable science-based approaches for leveraging hearing and balance to learn faster and more effectively. The auditory system. Decoding sound for cognitive gain. The auditory system is a sophisticated biological apparatus that transforms sound waves, fluctuations in air pressure, into meaningful neural signals. Huberman explains that this process begins at the outer ear, or pinna, a cartilaginous structure uniquely shaped to capture sound waves based on an individual's head size. The pinna amplifies high-frequency sounds such as squeaks or shrieks, channeling them into the ear canal where they strike the eardrum, a flexible membrane that vibrates in response. The vibrations are transmitted to the ossicles, three tiny bones known as the malleus, incus, and stapes, collectively likened to a hammer. This hammer strikes the cochlea, a snail-shaped, fluid-filled structure in the inner ear. The cochlea is critical for converting mechanical vibrations into electrical signals. It contains hair cells which are tuned to specific sound frequencies. The cochlea's structure varies in rigidity, with one end more flexible for low-frequency sounds and the other stiffer for high-frequency sounds. When sound waves ripple through the cochlear fluid, hair cells bend, triggering neurotransmitter release that sends signals via the auditory nerve to the brain. In the brain, these signals are processed across multiple stations, including the auditory cortex in the temporal lobe, where conscious perception of sound occurs. However, the brain's processing extends beyond mere perception. It integrates auditory input with other sensory data, particularly vision, to localize sound sources in space. For example, the brain calculates the time difference of sound arriving at each ear to determine whether a sound originates from the left, right, or directly ahead. The pinna's shape further aids in distinguishing sounds from above or below by modifying frequency patterns. This ability to localize sound is crucial for learning, as it allows individuals to focus on relevant auditory information, such as a teacher's voice in a noisy classroom. Huberman underscores that the auditory system's role in learning extends beyond processing spoken language. It modulates brain states, enhancing attention and memory formation through interactions with regions like the hippocampus and prefrontal cortex. Binaural beats, tuning brain states. Learning. One practical tool for leveraging the auditory system is binaural beats, which Huberman describes as a method to influence brainwave activity. Binaural beats involve playing two slightly different sound frequencies to each ear through headphones. For instance, a 200 Hz tone in the left ear and a 210 Hz tone in the right ear create a perceived 10 Hz beat in the brain. The difference between the two frequencies. This phenomenon, known as neural entrainment, synchronizes brainwave activity to match the beat's frequency. Brainwaves are categorized into bands, each associated with distinct mental states. Delta 1-4 Hz facilitates deep sleep and relaxation. Theta 4-8 Hz promotes meditation and light sleep. Alpha 8-13 Hz enhances calm alertness, ideal for recalling information. Beta 15-20 Hz supports focused attention and new learning. Gamma 32-100 Hz boosts problem solving and peak cognitive performance. Binaural beats in the alpha or beta range can enhance focus and learning by placing the brain in an alert yet relaxed state. Huberman cites peer-reviewed studies showing that binaural beats, particularly in delta, theta, and alpha ranges, reduce anxiety, which can otherwise hinder learning. They also show promise in managing chronic pain, though their primary benefit lies in fostering brain states conducive to studying or creative tasks. However, Huberman cautions that binaural beats are not a panacea. Their effectiveness depends on individual differences and the quality of the audio delivery. High-fidelity headphones and consistent use, e.g., 10-20 minutes before a study session, are recommended to maximize benefits. Importantly, binaural beats are one of many auditory tools, not uniquely superior, but effective, modulating brain chemistry to support learning. White noise, enhancing focus with caveats. White noise, characterized by equal intensity across all sound frequencies, is another auditory tool that can enhance cognitive performance. Often described as a hiss or static, white noise masks distracting background sounds, creating a consistent auditory environment. Huberman highlights studies, such as a 2014 paper in the Journal of Cognitive Neuroscience, demonstrating that low-intensity white noise improves performance on auditory working memory tasks by modulating activity in dopaminergic midbrain regions and the right superior temporal sulcus. Dopamine, a neuromodulator associated with motivation and craving, plays a key role here. White noise increases baseline dopamine release from the substantia nigra, a midbrain region, enhancing alertness and focus. This effect, known as stochastic resonance, amplifies weak neural signals, making it easier to process relevant information. For individuals with attention deficits, such as ADHD, white noise can stabilize prefrontal cortex activity, further boosting learning efficiency. However, white noise has potential downsides, particularly for young children. Huberman references research published in Science showing that continuous white noise exposure in infant animals disrupts the development of tonotopic maps, neural representations of sound frequencies in the auditory cortex. These maps, formed by cochlea's frequency separation, are critical for distinguishing sounds like speech. In infants, prolonged white noise exposure, e.g., from sleep machines, may blur these maps, potentially delaying auditory development. While not catastrophic, as children also hear varied sounds like voices or music, Huberman advises limiting white noise to low volumes and short durations, especially during sleep, to protect developing brains. For adults, white noise poses no such risks and can be a valuable tool when used judiciously. Playing it at a low level during study sessions can enhance focus by drowning out distractions without overwhelming the auditory system. The cocktail party effect, mastering auditory attention, the brain's ability to focus on a single sound source amidst a cacophony, known as the cocktail party effect, is a testament to its selective attention capabilities. Huberman explains that this phenomenon allows individuals to extract relevant auditory information, such as a conversation partner's voice, in noisy environments like a crowded party or busy classroom. This process involves both bottom-up sensory processing, detecting sounds, and top-down cognitive control, prioritizing specific sounds. Neuroscience research reveals that the brain creates a cone of auditory attention, narrowing its focus to specific sound waves by attending to their onset and offset. For example, to remember a name like Jeff, one should focus on the initial J and final F sounds to boost signal-to-noise ratio. This technique enhances recall by filtering out competing auditory input. The prefrontal cortex and superior temporal gyrus work together to direct attention and distinguish speech from background noise. Training this ability can accelerate learning. Huberman suggests exercises like listening to a podcast in a noisy setting and summarizing its content, which strengthens neural circuits for auditory attention. Such practices improve the brain's capacity to focus in challenging environments, making it easier to absorb and retain information. The vestibular system, balancing body and brain. The vestibular system, responsible for balance and spatial orientation, is housed in the inner ear alongside the cochlea. It comprises 3 semicircular canals, each oriented in a different plane: vertical, horizontal, and tilted, and otolith organs that detect linear acceleration and gravity. These structures contain hair cells that respond to head movements, pitch nodding, yaw shaking side to side, and roll tilting, by deflecting in response to the movement of calcium-based stones within fluid-filled canals. Huberman emphasizes that the vestibular system collaborates closely with the visual system to maintain balance and coordinate movement. For instance, when turning the head to locate a sound, the vestibulo-ocular reflex stabilizes the eyes to maintain a clear visual field. This integration is evident in simple experiments. Standing on one leg with eyes open is relatively easy, but closing the eyes induces postural sway, highlighting the visual system's role in balance. Vestibular stimulation, particularly through dynamic activities like skateboarding, cycling, or dancing, enhances balance and cognitive function. These activities involve forward acceleration and head tilting, activating the cerebellum, which regulates motor coordination and influences learning via outputs to dopamine and serotonin, releasing brain regions. Huberman notes that such movements increase neuroplasticity, making the brain more adaptable and enhancing learning in subsequent tasks. Practical applications for cognitive enhancement. Huberman's insights translate into actionable strategies for optimizing learning and focus. Use binaural beats strategically. Listen to alpha or beta binaural beats 8-20 Hz through high-quality headphones for 10-20 minutes before studying. Enhance focus and reduce anxiety. Incorporate low-intensity white noise. Play soft white noise during study sessions to mask distractions, but limit exposure to 1-2 hours and avoid high volumes, especially for children. Train auditory attention. Practice focusing on specific sounds in noisy environments, such as identifying keywords in a conversation, to strengthen the cocktail party effect. Engage the vestibular system. Incorporate dynamic movements like balance exercises, sports, or dance into daily routines to boost neuroplasticity and cognitive performance. Combine sensory inputs. Use multisensory approaches, such as listening to educational content while walking, to engage auditory, visual, and vestibular systems simultaneously.